Alrighty, guys, can you hear me again?
Yes.
Okay. Alrighty, are there any questions on all the stuff we did before the break? Or should we move on to the next one? Okay, we will do number 10 then. So number 10, show the camera. Number 10 is about, it's a play on the absolute value function. So problem 10. It's a play on the absolute value function, right? So the when you write a plus, this is the maximum of 0 and a, right? And a minus, this is, so if you want to take the min now, we're going to take, so this is going to be negative. And then you're going to put a minus sign in front of it. So then the absolute value is just going to be a plus plus a minus. And a is going to be a plus minus a minus. So this is what this question here is about. It's just a play on these decompositions. So when you talk about a straddle, that's a payoff at time capital N given by the absolute value Sn minus k. So now we use this property here. We can run, so we can use this property that the absolute value of Sn minus k can be given as you add them up. So Sn minus k, positive part. Right, so I should make it clear up here. This is also equal to a max of 0 and then minus a. So I can do the absolute value. I'm going to get a plus, and then the max here is going to be. I need to swap these k minus Sn positive part. And so we see here is, excuse me, this here is the call, right? And this here is the put. And so what you're given in the problem is that you're given that the price, given that the call price equals, what was it in the call price, 6, and you're given that the put price, what was the put price in the problem, it was 5. Right, so then the straddle is 11. So that's how you, if you're given put and call prices, which we are in this problem, you can recognize that the payoff of the straddle is simply just a combination of the calls and the puts. And then that's all there is to it. Any questions on this part? So the next one, this is about pricing payoff that involves the min and the max. Number 16. This is problem number 11. So you're given specific values. So you have a 2-period model. You're given U's and D's. U is 2, D is a half, and R is 25%. The initial stock price is 8. The first question is compute these p tilde probabilities. So at this point, I think I do remember the formula. It was U minus D. It was 1 plus R minus D. We've had that many times now. And let's just plug in what we end up getting here. This is 1 plus R. This was 1.25 minus D. That was a half, divided by U was 2. D was a half. So I think we end up with what upstairs will be 0.75, downstairs will be 1.5. So this ends up being a half. This configuration up here we've seen many times. So that was the first question. So the second question is, we're looking at this derivative that we want to try to price. So the payoff at time 2, this is the end, right? The payoff at the end is given as this M2, which is the max of S0, S1, and S2. And then minus the min is called L for lower. So we take the min of the same quantity. Right, so the payoff is going to be that difference. So what we're looking at is, here's time 2, here's time 1, and here's time 0. Right, so we're going to get this payoff out here. This is M2 minus L2. Right, and this is random. And so what we're interested in is moving this back. So as before, we move it back to here, and we move it back to here. Now, how do we do it? We're in a binomial model, so we can also build the tree. That's the tree that supports this. So we'll have S0 was 8. And then it can go up to 16. It can go down to 4. And you can do the same thing. It can go up to 32. And it can go down to 8. And it can go up to 8. And it can go down to 2. So what does the payoff look like? So this is the stock. Right, so we also want to have the derivative. The payoff here is going to have, there will be 4 possibilities. Right, so we have heads, 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 tails, tails, heads, tails, tails. So if we look at the payoff if heads, heads, what's that? I get a head here and I get a head here. What is the maximum? And the max is going to be along that path, right? Heads and heads. So the maximum is 32. What's the minimum? Well, that's going to be 8. So that will be 24. And so if we instead have heads, tails, if we go from heads and then tails, then the maximum is 16 and the minimum is 8. And if I instead do tails, heads, so I go down and then up, the maximum is going to be 8. The minimum is going to be 4. And then last one is tails, tails. So the maximum is 8. The minimum is 2. Right, so here it's a good idea. It's a good idea to draw all the possibilities. Don't make them recombining, because you can see HT, the payoff of the derivative in the HT is different than the TH combination, right? 8 and 4 are not the same. Okay, so that's the payoff we get out here at the end. So we're going to get 24, 8, 4, and 6. So as usual, we move it back, like we out here. Time 2, we move it back once. So we're going to move this payoff back, and we're going to move this payoff back. How do we do it? So the tree that we're looking at, so this is a derivative. Here we're going to have 24 and 8. What is the value there? Right, and the same thing, we also need to do it for the other one. So we have 4 and 6, and what's the value here? So let's write out what the value is. Well, we take the average. The risk neutral probability is d/1/2. The risk neutral probability is d/1/2. So we take half here. We need the interest rate, 25%. So this is 1/1.25. And then we add up 24 and 8. And this becomes, if my calculations are right, 12 points, 12.8. So that was the value we have in that node. And then there's this node, do the same thing. Interest rate, probabilities, payoffs. This will be, I think, 4. And then finally, this was at time 2, this is at time 1, but we have to get all the way out to time 0. So we take these two, we combine and do the same calculation. So 1/1.25, 1/2, and then 12.8 plus the 4. This will be, if I did it right, 6.72. Any questions on this calculation? The next question says you should figure out what the replicating portfolio is. How do you invest? Right, you have to trade a number of shares here, a number of shares here, and a number of shares here. So how does one do that? So you need to set up these replicating equations for this particular problem. It is asking us to do it. It's asking us to do it when the first coin toss is tails. So it's interested in this component down here. We've been asked about this one down there. Okay, so so the replicating property is, so we're sitting here, we need to replicate these two. Okay, so what is that? Well, let's just remember, I want my wealth at time 2 to be this payoff. I want the payoff at time 2 to be of the wealth. I want this to be equal to M2 minus L2. Yeah, and so we need to remember, how do we link? Like I know here that the wealth that I should have, this doesn't look right to me. Okay, so how do I set up the replicating? These two here are going to be 4 and 6, but you'll break into two equations. We're going to write that this thing here is, maybe we should plug in what is x2 here. What is this x2? This is x1 plus delta x2. If you don't remember these formulas, there's another way to do it. We did that in class. We will say here that the wealth at time 2, this is the number of shares in the bank at time 1 times 1 plus r plus, and then what we have here would be number of shares times, to write out the price process. So let me write out S20 plus, and then the number of shares in the stock times the stock price. So this is equal to M2 minus L2, and we can plug in stuff over here. We can write this in terms of delta 1, and then the bank account is going to be, well, 1 plus R times S10 plus delta 1 is 2. This is M2 minus L2. So then we can use the definition to bring these two together. This is the same. The same 1 plus R. And then what would I have here? This would be x1 minus delta 1 S1 plus delta 1 is 2. So now we're almost there. So what are the unknowns? Well, x1, if I am in a down state, this is going to be 4. The value of the downstairs, this is going to be 4. But this one here would be my 4. This one here, this would be 1.25. Delta 1, this is the unknown. S1 in the down state, this would be 4. Now S2, that could be 2 values, and this one over here could be 2 values. Okay, so we're going to break this into 2 equations and 2 unknowns. So let's try to do that. I'll have 1.25 times 4 minus delta 1 times 4 plus delta 1. And now in the up state, the stock is going to be 8. And what is the payoff of the derivative in the up state? That was a 4. That was up state. So we also need a down. Well, the first values here, they don't change. This is just related to the money market. So here I have 4 minus delta 1 times 4 plus delta 1. But now S2 is changed because in the down state, this is equal to 2. And the payoff of the derivative, that's going to be 6. So those are the 2 equations that I need to solve. And if you remember the discussions we had in class, like you have two equations, there's only one known, so you have to have a miracle for this to work. And let's see if we have a miracle here. Let me try to write it out. Maybe in the interest of time, let me write it out in Mathematica. Mathematica, see if we can get it to work. If you don't get it to work, there's a mistake somewhere. So can you guys see my Mathematica code here?
Yes.
Yes, let's try to write it out. So 1.25 times 4 minus delta 1 times 4 plus delta 1 times 8. I want this to be 4, and I want to solve for delta 1. That was if I solved the top equation. Now what happens if I solve the bottom equation? So we need a miracle. The first part, this is the same because this is stuff that's related to the money market account, but here it changes. Right? Instead of 8, I get 2. And instead of 4, I get 6. And I solve that. And the miracle does happen, right? Delta 1 is minus a third. So as we talked about in class, this might seem like a miracle, but it's really not a miracle at all, because this is how it was all created. So it does work. We do get here that while we have two equations and two unknowns, they are consistent. And this here is the same thing as saying that delta 1 is minus 1 over 3. Are there any questions on this part? Are we all good? Very often when you have chaos like this one here, where we have the max and the min involved, it is when you draw the tree for the stock, very often what you need to do is to allow for all the branches. And this is related to this Markov property that we talked about earlier, that by themselves, these max and mins, they are not Markovian. And that means you have to keep track of everything. And therefore, it's just a good idea, even though you don't have to draw these two branches here, you could combine them. When it comes to the actual derivative, you need these branches typically to be separated out, because 4 and 8 are not the same, even though here you have the same. Right? And the reason for that is this lag of the Markov property. So whenever you see a max and a min, do yourself a favor and draw the tree with all the branches. Don't make it recombining. Any questions before we move on? Okay, so the next couple of questions, to save a little bit of time, I think the next couple of questions 12 and 13. If you have the problems, I can also show you my copy here. Problems 12 and 13. This is more mathy. I think it'll be better for us to do the problems that are related to the binomial model, unless, I mean, does somebody really want to see 12 or 13? If not, let's skip those for now and then go down to let's go down to number 14. right? There's solutions to all these problems too. And if you see typos in the solutions, just let me know. I'll correct them. Anyway, we're looking at a binomial model, which is more or less the same as what we had before. So we have a we have U is 2, D is a half, and R is 25%. The initial stock price is 4 this time, but you know these ones here, they combine, so P tilde becomes a half. And now the payoff is a little bit different, but it's not that different. It pays out Vn. This is going to be the max, so it's the stock minus the min of all the previous stock prices, S0, S1, all the way up to and including S capital N. Like, so again, there's a min. So when you start looking at trees, make sure to break out the tree into all its possible branches. Don't combine them, don't recombine them here, because the min and the max, you don't have this nice macro property that S has. Okay, so then the question is, if you want to price this, so price of the payoff Vn at earlier times. So that'll be time 0, time 1, all the way up to time n minus 1. How do we do it? Well, there's a hint that says that find functions fn, find functions fn such that the value or the price, the value of Vn at an earlier time, so say at time n, but the value of this Vn at an earlier time is given as, then there's a formula. It says you take the stock price at that time, and then you apply the function, and you apply the function to Mn divided by Sn. And your job is to figure out how to calculate Fn. And it says you can use this backward recursion, which is what we also did in class. Right, so we're going to find a backward recursion for functions fn minus 1 all the way down to f0. Right, so the first order of business is you always start with the terminal one, because that's the guy we have here. Like, what is M here? M is that running min, Mn. Mn is this min of the stock price up to time in. So what would we like? What would we like here? We need Vn. So we start out here with Fn. How do we get Fn? Well, we know we want Fn times Sn applied to Mn divided by Sn. We want this to be, well, we want this to be Vn. So Vn was Sn minus, then this min, this was Mn. So that's the requirement. What should Fn be? So we solve for Fn. Fn is equal to, what would it be? 1 minus 1, there's a minus sign, 1 minus x Let's just do a sanity check here. Sanity check, if I take Sn times Fn, this is 1 minus, and then instead of x, I'll have Mn divided by Sn. What would it be? Sn minus Mn. Yeah, it works, right? That's exactly what we want. Okay. So how do we get the next one? How do we get the next one? So the next one we want to get is Fn minus 1. Well, we roll it back. We roll it back and we compute the conditional expectation. We compute the conditional expectation, the discounted value. We're going to go from time n to time n minus 1. So we roll it back once. And so here we need Fn Sn Fn of Mn divided by Sn. Given the sigma algebra, the first n minus 1 coin flips. This is the payoff. This is the payoff. This here is my Vn. So we take the payoff, we roll it back one period. So we are standing as before, right? We are out here time n. This is where we get the payoff. Sn f. Write this more. Getting the payoff Sn f applied to m over S. So again, the payoff over here, we want to roll it back one period to n minus 1. And the way we do it is we compute the conditional expectation, we discount one period, and we move it back. Okay. And how do I compute this mess here? Well, it looks pretty bad, but it's not like horrendously bad, right? The goal is to write this here as, that's what the statement says, that you can write this here as, this is the question, you can write this as Sn minus 1 of Fn minus 1 applied to that ratio at an earlier time. But for what function f? How do we find this function such that this is true? Well, as we've done a few times, right, the way that we go about doing this is using the independence lemma. So the way to go about doing this is to use the independence lemma, right? Calculate the top part using the independence lemma. So this is a constant, so you can go outside. And then we can start putting in these values for Sn. We start putting in these values for Sn and also for Mn. Okay, so let's try to do that. So we write this here as, now there's a long calculation coming. So this is 1 over 1 plus r. Conditional expectation. And this is where I like to do a few steps instead of just skipping ahead, because it's so easy to make mistakes. So Sn, I can write this as Sn minus 1, and then I need the last coin flip, psi n. That was a definition of what the stock price is in a binomial model. Then I have my function f. What do we have downstairs? Well, we use the same as what we had here. This is Sn minus 1 psi n. What do we have upstairs is the min. Right, so that's the min. That's the min, right? So the min can be calculated as the min of, well, the min up to time n minus 1. So that'll be Mn minus 1 and then Sn. Again, Sn is expressible as Sn minus 1 times psi n. Just as we replaced Sn here with that value, we can do the same thing here. And then the condition on the sigma algebra up to time n minus 1. Okay, so what are we in for now? We will try to use the independence lemma. So there are always these two things that has to hold. You have to have some stuff that's measurable, and then the rest has to be independent. And what is good here is that the psi n's, they have the independence property. So psi n is independent of these first coin flips. So that's good. And the other thing that is good is that Sn minus 1 and Mn minus 1, they are measurable with respect to the sigma algebra we condition on. So that is all it takes to get the independence lemma going. And so this one here, he's easy, he's being multiplied. He can go right outside. So I'll have Sn minus 1 out there divided by 1 plus r. And now let me use the independence lemma on the remaining parts. This guy here, he is independent. I'm going to keep him. I'm going to take the average. And then I have my function applied to this min. Min, that was measurable, so we replace him by a dummy. Let's call it y. And then here I have Sn, that's going to be Sn minus 1. So Sn is going to be replaced by a dummy. This one was independent. And then down here, I'll divide by Sn. The dummy here was x. And I'll have psi. This is all inside the function Fn. Okay, so I perform this calculation, and when I'm done with it, I replace the dummies x and y by x was Sn minus 1, y was Mn minus 1. It's quite similar to what we've done before. It looks messy, but it's not that different. We've seen a few times today. And now I'll take the average over the size, and the size can only take two values, u and d. The size can only take two values, u and d, and so that's why this is Sn minus 1 divided by 1 plus r. Psi can take on two values, so we'll have a p tilde times u, and then it'll be Fn. Inside here, I'll have a min, and I can move x and y together, but I want to do that. So for the min, y divided by x, put that inside. X's will cancel out. Here I'll have psi n, take the average, so this is a u divided by u. What else do we have? Is that it? I think that's it. Plus, and then 1 minus p tilde. Fn, and then the min, do the same y over x. And then instead of u here, we will have a d. There should also be a d outside there. And then it will be d divided by t. So that's our function. And let's just, so the goal was to write this as this mess here. Is this true? So is this equal to, and of course I need to pull in what x and y are. X is equal to Sn minus 1, y is equal to Mn minus 1. Here really equal to a function Sn minus 1, Fn minus 1 applied to Mn minus 1 over Sn minus 1. Well, we have to compare. Sn minus 1 is good because that's the same thing that's down here. So they will cancel out. So these two cancel out. Okay, and what about x over y? Well, y over x. Y was Mn minus 1, x was Sn minus 1. So that looks good. We do have this structure. We have that Fn minus 1. I don't know what variable that's left to use here. It will be like maybe call it, I don't know, z. This is going to be given as 1 over 1 plus r p tilde u, and then Fn applied to the min, and then here's our z, and then here's u divided by u. That was the first one. I think u is equal to a specific value in the problem. U is equal to, so this quantity here, this is equal to 1 over 1.25. P was a half, u was 2. So we can plug all those values in if we so desire. It's 1 minus p tilde, and I have a d. D was a half, I think, in the problem. And then the same thing, Fn. And then you have the min with z d divided by d. That's your function at the previous time. The questions on this? It's a mess, but in the end you get this function then. And then there's nothing specific about this. This can be iterated. You can iterate. So given Fn plus 1, you'll get Fn of, say, z. You can iterate this, so you'll get Fn of c. This will be 1 over 1 plus r. P tilde u, and then instead of Fn, you have Fn plus 1. Take the min, you can move the u inside if you want. So this is c over u and 1 plus 1 minus p tilde d Fn, and again you can move the d inside if you want to. So this would be the min c over d and 1. And this way you're going to get it all the way back to times 0. Which is where you find the price that you're interested in. Are there any questions on this, guys? You were very quiet here after the break. You're a lot more questions before the break. Does this make sense to you guys?
Yes.
Yeah. Alrighty. We have a little bit of time left. The next question asks us to plug in numbers and see that you can actually get numbers out of this. I'm going to skip that one. I would rather spend the little bit of time we have left on the last couple of questions. Questions number 16 and 17. Questions 16 and 17. So number 16. It's a familiar setting. We're given jointly normals. So x and y. Got means 0 and variances, covariances being 1 on the diagonal and then some row outside the diagonal. So standard normals individually, standard normals, and then you also jointly with correlation row. And then you're asked to compute this conditional expectation of x squared given y. And it's we have seen stuff like this in class that we could decompose. We could decompose x. So it's quite similar to what we've seen in the binomial model. Like we need to be able to express x in terms of something that involves y, and then something that is independent of y. So we want to decompose x into a y component and something that's independent of y. It is very similar. It's very similar to what we saw over here. It's a mess of a calculation, but what we want to do is we want to decompose this guy and what we have in here into something which is measurable with respect to this thing, the sigma algebra, and then something that is independent. And as soon as you have that structure, you can use the independence lemma, right? Those are the two properties you need. You need something that's independent and something that is measurable. So what we're doing here is nothing else. But now there's just no, how would one go about doing this? We talked about it in class that there was a way to do this. And we said, why don't we just try this y perpendicular, try to call him, try to define a random variable, which is x minus, and then this row, the correlation up here times y. Well, so then definitely you will have x is decomposed into something that involves y, and then this y perpendicular, right? So you have the x is equal to rho y plus y perpendicular. What remains to check is that this y perpendicular is independent, right? So we should check here that y perpendicular really is independent of y. And this is where joint normality comes in. We're going to use now here that y perpendicular and y, they are jointly normal. Right, and it's the word jointly we're looking for here. We're not looking for them individually to be normal. So it's the word jointly normal that's going to make this work. Because then you have that independence is the same thing as being uncorrelated. So then you'll compute the expectation of y times y perpendicular, right? This is the covariance. It's the covariance because you have zero mean, right? So we don't have to subtract away the product of the expectations because that's going to be zero. Okay, so let's work out what this one here is. You take y, and then you plug in the definition of y perpendicular, x minus rho y. And we factor out, so x times y, that's going to be rho, minus rho, and then the expectation of y squared. Well, the expectation of y squared, that's going to be the one you have down here. So this is going to be 0. So you have this, so now we're good because now we have the structure. And this structure here is what will then allow us to compute this thing. We now have that decomposition that we're looking for. We have x here. We write x here as rho y plus y perpendicular given y. And now we know y is going to be measurable. Y perpendicular is going to be independent. So we use the independence lemma. Write it down here. We're going to use here, this is the independence lemma. We're going to need two properties. We're going to need that y is sigma y measurable. And the other one we're going to use is that y perpendicular is independent of y. These are the things. The last one is what we established here. This is what shows that you have independence. So now we can use the independence lemma, and it will tell us that this expectation over here can be calculated as the unconditional expectation. You replace the measurable part with a dummy. So let's say rho x plus y perpendicular squared. And then you put x equal to y when you're done. So again, we go through the same steps that we went through a few times today. And what we'll get here is, let's work out what the expectation of rho x plus y perpendicular is. We'll factor out the square. So this is rho squared x squared plus 2 rho x y perpendicular plus y perpendicular squared. What is this expectation? Well, we're going to need the mean and the variance of y perpendicular. There's no way around it. We're going to need the mean and the variance. So if I compute the mean, I think we already had that one. But this is going to be the mean of x minus rho times the mean of y. Well, that's 0, because both x and y had 0 means. And then we need the second moment, the variance. And the way we go about doing that is we're just going to plug in y perpendicular in the formula. So this is x minus rho y squared. And we factor out as before, x squared, rho squared, y squared, minus 2 rho xy. And so now we're going to be working over in the variance covariance matrix. You have x squared. That's the one you have up here. This is the variance of x. That's a 1. Then you're going to have rho squared times the variance of y. That's the second moment of y. What you're going to find down here. And then you're going to have minus 2 times rho. And then the expectation of the product, well, that's going to be what's off the diagonal. So it's going to be rho squared. And you end up with 1 minus rho squared. And that's my variance. So from this, we combine that we can conclude that y perpendicular is standard normal, mean 0, and variance 1 minus rho squared. And I think that's all we need to finish off the calculation up here. We get rho x squared, and you get the expectation of y perpendicular. That was the 0. We're going to get the second moment, 1 minus rho squared. And then we just have to replace the dummy with y. Okay, so all in all, the conditional expectation of x squared given y is going to be this function up here, rho squared y squared plus 1 minus rho squared. So if you know that x and y are jointly normal, and you know what y is, then your best estimate of x squared is going to be this formula here on the right. And this is y measurable. Other questions on this part? So variation of this decomposition that we had discussed in class, and I think there was also a homework problem about it at some point. I forget how many weeks back, but at some point there was a question related to it. Any questions on this part? If not, let's do the last problem and then call it a day. The last one is number 17. Problem 17. So it's an n-period model. So you have your size. So you have your size up to capital N. The IID, you'll take on two values, U and D. And then in between here, you have your 1 plus R. Now we have a derivative. That pays out. It pays out here Sn plus root Sn. What we want to know is, right, so this is random. So we don't want to move this payoff one step back at a time, all the way back to time 0. And see, if had it only been this one, it would have been easy, right? The payoff this would just be the stock. Like had it just been Sn, it would have been easy. It would just be the stock at time 0. But here we have this square root, which is this nonlinear function. So the complication is coming. The complication is coming from the square root. If I look at the price, so if I look at the price at time n minus 1, so we go back 1, I'll have to compute the conditional expectation of the discounted payoff. So this is 1 plus R Sn plus root Sn. And then the first coin flips. So the first part here is, this is a nice one because you have a martingale. You know that the discounted stock price is a martingale. So this here will be Sn minus 1. Now the second part is harder because there's a square root. The square root is a concave function. So there is a Jensen inequality effect. You cannot just pull the square root outside. But let's try to compute it. You can put 1 plus R outside. And then we can compute as before. You decompose Sn into something that is measurable. So this is Sn minus 1, and something that is independent. That's going to be your psi n. And then you condition. So here we use the martingale property that if I take the stock price, I discount it, compute the conditional expectation, I'm just going to get the current stock price. The second part here, this is harder, but at least we got to decompose. So we can pull out the square root of Sn minus 1. And then what remains is the square root of psi n, but that's independent. So we can simply just compute its expectation. And now given that, this expectation here, this will be p tilde, square root of u, plus 1 minus p tilde, square root of d. If we move it back one more time step, we'll take this payoff, we'll discount it, we'll move it back to time 2. What will we do? We'll have to move the two components. So it'll be Sn minus 1, 1 plus R, and then it'll be Sn minus 1. And then the other thing, you have the square root, Sn minus 1. Then p tilde square root u plus 1 minus p tilde square root d. And then we have the condition. I'm just going to write f here. Condition Fn minus 1. Fn minus 1, this is all we write. If it's Fn minus 2, I'll be moving back to n-2. And the first part, same as before, discounted stock prices will be a martingale. So here we'll have Sn-2. Then over here, this is a constant coefficient. So all that can go outside, 1 plus r squared, p tilde square root u plus 1 minus p tilde square root d. And then what we will have in here is we want to decompose Sn-1 into Sn-2 times psi n-1 and condition on Fn-2. And now we have exactly the same scenario as before. The first one is measurable, the second one is independent. So you can see what we want to get. It's going to be Sn-2 plus this 1 over 1 plus r squared. And then you're going to get the square root, 1 over the square root of Sn-2. And then you're going to take the average over the rest. And when you do that, you're going to get exactly this coefficient here squared. And then you can keep going all the way down to time 0. You're going to get the expectation of 1 over 1 plus r to the nth of Sn plus root Sn. This is going to be the first term will just be S0. The second term be 1 plus r to the nth, 1 over square root of S0. And then you'll have this p tilde root u plus 1 minus p tilde root d to the power n. And so this here is the price. This here is the price that you're paying out at time 0 for getting the pay of Sn plus root Sn at time capital N. Yeah, are there any questions on this?
Professor, just a general question. While you're presenting it, it seems very clear and elementary and very doable. Do you have any recommendations as to recalling the steps involved to get it to that?
So it's deceiving, right? I mean, I've done this for so many years. So this is not easy. Right? It is just not. This material here, this is a challenge. Students, they end up being able to do it, but I am never going to refer to this material as something that is easy and doable. It is something that one can master over time with a lot of practice. So there's no way around it. You have to try to practice doing this, write these arguments out. Maybe in your homework, you did not fill in all the steps. Make sure that you know how to fill in these steps. Like, where is it that you're using independence? Where is it that you're using that something is measurable? Yeah, like I will ask you questions from the homework, but at this point you can see that there is like a general structure. When you compute these conditional expectations, you always have to break these random variables into this specific structure with independence and measurability. And that's because this is the only way that we know how to do this at this point. When you move into 622 and 623, then there'll be other ways that we can compute these conditional expectations using like using a computer, using simulation, or using PDEs and ODEs, but we're not doing that in this class. So at this here, the only way that we know how to get our hands on these conditional expectations is by breaking it up into something that is measurable and something that is independent, and then using the independence lemma. So you need to be comfortable doing that. And there are lots of problems you have to practice on, because all the problems evolve the same couple of steps.
Thanks, Professor. That makes sense.
Yeah. But try not to memorize it. This is because if you memorize it, then it just takes a little twist. Like I ask you something that is a little bit different, and then it can throw everybody off completely. And so be careful about this memorization. This is not a good idea. And so can I give an example of something where that would be the case? And say, yeah, I can do that. Like imagine this problem here. You being asked a problem of this sort. So what could I ask you? Well, I could ask you, well, instead of this square here, what would happen? Like, so a variation. And I think I actually asked students about this last year, right? A variation on number 16. Like, what about if you were to compute, say, sine of x given y? What is that equal to? Or you can put in your own favorite function here. It doesn't have to be sine, tan, cosine, whatever you want to put in there. How would you compute this? Now, so that's what I mean by memorization. It can be, so please try not to do that. Instead, you should see this. Okay, I have a function, I have y. What do I need to do is I need to decompose x into something that has to do with y, and then hopefully something that is independent. So this structure here still works. Right, so how do I apply it over here? Well, you're going to be having these two properties, and then you're going to be using the independence lemma, right, and then try to work this out. Are there other questions? So there was one of you who asked about the CDS contract. We are out of time. Can I ask that student to either come to office hours on Friday or office hours next week, and I'll be happy to help out trying to get this CDS contract settled. It's just it's not going to be CDS contracts we'll discuss next week. So I felt it was better to spend the time and energy on these things here that are more relevant for next week. Are there any questions before we stop here? Otherwise, I hope you got something out of it. If you have questions, the way to do it is to come to my office hours. It's just this stuff here, it cannot be discussed over email. It is just impossible. So if you have questions, come to my office hours on Friday morning. I'll be happy to help out as best as I can. All right, I'll see you later, guys. Have a good evening. Have a good day.
Thank you, Professor.
You're welcome.
Thank you.
You're welcome.
Thank you.
You're welcome.